Well, welcome back, everybody. As promised at the end of last lecture, today we're going to take a look at matrix algebra. Okay, and I think overall this will be a shorter set of lectures, but we're going to kind of be looking at the question of what makes two matrices equal. Okay, because the moment that you have a notion of equality, right, we can then on top of it build a notion of addition and subtraction, in this case multiplication. We'll see, I think at the beginning of next week, we'll see that you can't actually develop any idea of division, which I think is kind of interesting. But before we get into any of that, we do need to ask that first question, right, of what makes two matrices equal. Okay. And, it seems like there is an obvious answer, right? So let's say we'll need two matrices, right? In order to answer this question, right, we'll need to have two of them, right, for them to be equal. Okay, so let's say we have some matrix A, right? Matrices are usually written with capital letters for the name of the matrix, and then lower case letters for the entries, right? And B is Bij. Okay. Let's say that they're both M by N matrices. Okay. So if you have this setup, well, then how would we expect to quantify that A equals B, right? They're the same shape. So we would say that they're equal if and only if, remember this is, our little double arrow means if and only if, Aij equals Bij for all I and j, right? So this definition is exactly what you'd think, right? Two matrices are equal if each of their corresponding entries are equal, okay? And so you might have something like this, right? We can, we can bring up a couple of matrices here. Let's say this one is the square root of 4, 2 squared, maybe e times pi to the 0, maybe 0.5, 2, and 1 minus 1, okay? Here's our second matrix, right? Let's say it's 2, 4, 1, 1 half, 4 halves, and 0. Are these two matrices equal, right? Well, they're the same shape, right? They're both 2 by 3 matrices, which bodes well. And then we just need to sort of go through element by element and inspect all of them, right? The square root of 4 is equal to 2. 2 squared is indeed equal to 4. E times pi to the 0, well, that's 1 because anything to the 0 is 1. 0.5 is 1 half. 2 is 4 halves, and 1 minus 1 is 0. So these matrices are indeed equal. Okay. What about this one? Let's say we have 1, 2, 3, 4, 5, 6. Okay. Let's say this matrix is 1, 2, 3, 4, 5, 6. Are these two matrices equal? Well, if we sort of look at this, we can see some similarities, but this is a 3 by 2 matrix and this is a 2 by 3 matrix. Okay, so they are not equal, not in the slightest. There's no way for them to be equal. They're different shapes. There is actually a relationship between these two matrices, though. If you were to imagine taking this one, right, sort of like sticking a pin in this point, and then like flipping the whole matrix over this axis, right, then you would get this guy, right? This is an operation called the transpose, right, where the rows become the columns and the columns become the rows, okay? right? We're sort of flipping it, right? We're fixing this top element and flipping it along this sort of line right there, okay? So now that we have this notion of equality, right? Now we can talk about what the sum and difference equals, right? So let's take a look at that. Take a look at sum, difference, and a new sort of thing that we get when we're working at matrices called the scalar product. Okay, this is different from standard multiplication, or at least standard multiplication of matrices. You'll see why in just a second. Okay, but to do this, we'll need a couple of things. We'll need a matrix A. We'll need a matrix B, and we'll need them to be the same shape. Okay, be m by n matrices. And we'll say some little c in R. Okay, this little c we call a scalar. Okay, hopefully you'll see why in just a second. But this scalar is distinct from these matrices, right? Which are these rectangular arrays. These kind of multi-dimensional objects. Whereas this scalar is just a single, element from the real numbers. Okay, and here's how we calculate these, right? And it follows pretty much exactly how you would expect, right? So A plus B, because they're the same shape, right? Right. You just add each of the entries, right? In the 3, 5 entry of A plus B, you add the 3, 5 entry from A to the 3, 5 entry from B, right? It follows exactly how you'd think. If you want to subtract these guys, right? If you want to subtract A minus B, well, then A minus B, you do it element by element, right? That's the really nice thing about these sums and differences, is they're all done element by element, okay? Now, what is this scalar product thing? Okay, so we calculate C times A, right? C is our scalar, and A is our matrix. And we do that by CA. Once again, we kind of do this element by element, right? C essentially gets distributed into our matrix, and you multiply every single element of the matrix by this number. Okay, and what that has the effect of doing is it scales every single element of this matrix by a factor of C, right? That's where it gets its name, right, of scalar. Okay, so let's do some examples of this. Okay, so we'll need a handful of matrices for this. So let's grab some matrices. Okay, so let's say A is 2, -3, a little clearer, 3, 0, 5, 7, 1/2. Let's say B is 1, 0, -3, 1, 2, and 2. We'll say C is 7, -3, 0, 0, 1, 5. And then finally D is 6, 0, -6, 8, 1, 9. Okay. And we want to calculate the following. We'll do A plus B, C minus D, A plus C, and 5 times A. Okay, so we can do these one at a time, right? For A plus B, we'll need our matrix A. And we'll need our matrix B, 1, 0, negative 3, 1, 2, 2. And we're going to add them element by element, right? So we're going to get a 3 by 2 matrix at the other side. Our first element is going to be 2 plus 1 for 3. Going over, we have negative 3 plus 0 for negative 3. 0 plus negative 3 again is negative 3. I see 5 plus 1 is 6. I see 7 plus 2 is 9. And I see 2 plus 1/2 is 5/2. Okay. What about C minus D? We'll need our matrices. 7, negative 3, 0, 0, 1, 5. And we're subtracting 6, 0, negative 6, 8, 1, 9. Okay. We're going to get a 2 by 3 matrix out the other side here. So 7 minus 6 is 1. Negative 3 minus 0, well, that's negative 3. 0 minus the negative 6 is positive 6. 0 minus 8 is minus 8. 1 minus 1 is 0. And 5 minus 9 is negative 4. Okay. Turning our attention to the next one, we're being asked to calculate A plus C. But wait, I know that this isn't possible, right? And that's because we have a 2 by 3 matrix here. We have a 3 by 2 matrix here, right? Addition here is not defined, right? And so we cannot perform that addition, okay? Turning our attention to the last one, we're being asked to calculate 5 times A, okay? So we'll write down our little scalar and then our matrix. We have 2, negative 3, 0, 5, 7, 1/2. And if you remember, when we're doing this sort of scalar multiplication, right, we're simply distributing this 5 into each of the components, right? So we have 5 times 2 is 10, 5 times negative 3 is negative 15, 5 times 0 is 0. Looks like we have 25, 35, and 5/2. Okay, nice and simple. That is our result. So now that we have these ideas, the question is, do any of our handy properties that we sort of got used to when we were doing algebra in the real numbers, do any of those carry over here? And it turns out, for addition at least, many of them do. Okay. The next part of this lecture will have to do with matrix multiplication. And we'll see we lose some of the properties, but almost all of the nice ones stay. Okay. So let's look at some properties of addition and scalar multiplication. Okay. One of the nice things is that subtraction and addition are in a lot of ways the same thing, right? You're just adding the negative. Okay, so when we say addition, we also mean subtraction, right? Because you can always find, the negative version of a matrix. So we'll need some matrices. So let's A, B, and C be m by n matrices. And we'll grab little c and little d, real numbers. Okay, so those are going to be our scalars. And there's 3 properties that I want to draw your attention to, and those are as follows. The first one is the commutative property, right? And this is one of our favorites for addition, and that says that A plus B equals B plus A. right? Nice and simple when we're adding, right, because it's happening element by element like that. We can switch the order as necessary, okay? The next one is the associative property, which arguably is a lot nicer even than when things commute, because imagine if you always had to write all of these parentheses, right? And the associative property says that if I'm adding these three, I can add A and B, or I can add A and C rather, and then add A, or I can add A and B first and then add C. We have a similar property for our scalars. It turns out you can do C times D and then multiply by A, or you can do C and multiply that into D times A, right? And you can go either way. You can freely reassociate like that, okay? Our last property is the distributive property, okay? I'm sure that's no surprise. So if I'm adding my scalars like this, and then I'm multiplying by A, well, that's the same as multiplying that A in, right? CA plus DA, okay? And it goes the other way too, right? If we're multiplying our scalar by some matrix addition, right? Well, then we can go C times A plus C times B, okay? One thing that I do want to draw your attention to really quick that I think is really interesting about this statement, right, is this addition, right? Think about where these two additions are happening, right? This addition is happening in the real numbers, right? This is real number land addition, okay? This addition is happening in matrix land though, okay? And that's what's so nice about this idea of scalar multiplication is that, the real number addition and the matrix land addition, they talk to each other, okay? But once we have these properties, what can we do, okay? Let me give you an example of one of the really cool things we can do. And that is we can solve equations with this, right? Our indeterminates were, previously these sort of, variables that when you were solving a problem, they took on one value, right? But not so anymore, right? You could have a matrix equation that was something like this, 2x minus a equals b, where say A is this matrix, 2, 3, minus 5, 1, and B was this matrix, 4, negative 1, 1, 3. Okay, so I can solve these matrix equations, right? Which is really, really cool. And here's how we'll go about doing this. Why don't we solve for the indeterminate x in terms of a and b, and then plug in our matrices, right? We can add a to both sides of this equation, right? Adding our matrix A keeps it equal, right? Just as it did when we were doing, algebra in the real numbers. So we're going to get b plus a, okay? I can multiply both sides by 1/2, right? That's going to clear this 2 and introduce a 1/2 to this side. So let's go ahead and do that. We have 1/2 times b plus a, okay? But I know b and I know a, so I can solve this, right? This is going to be 1/2 times 4, negative 1, 1, 3, plus 2, 3, minus 5, 1, okay? Our addition here is going to happen, element-wise. So we have 4 plus 2 for 6, minus 1 plus 3 for 2, 1 plus negative 5 for negative 4, and 3 plus 1 for positive 4. Okay, but now we're multiplying by 1/2, right? And this is a scalar multiplication. So what we can do is we can do this element by element, right? Looks like we're going to get 3, 1, negative 2, and 2. Okay, just like that, we've solved our matrix equation.